Hello, everyone. So today should be a pretty short day. It shouldn't be too bad. It's pretty much just using all of the information that we've learned so far and adding one new step to it. Um, we do have our first test coming up very soon. I will give you more information about that very soon. If I haven't already, I probably have. Um, so let's jump right into it. Again, this should be pretty short, shouldn't be too bad. All right, so we are talking about a topic called implicit differentiation. So before I get into this whole problem-solving strategy and all of this, I just want to briefly introduce this idea of implicit differentiation. So I'm going to go ahead and start with this little note down here, and then I'll get into the problem-solving strategy. So we use the idea of implicit differentiation when there's no way to nicely solve for our function y. Y is always in terms of x, but typically we have like y equals x squared, y equals the natural log of x, anything like that. Sometimes we don't have functions that look like that. Sometimes we can't necessarily separate our functions. We could have y cubed x plus xy plus 3, and there's no way of actually getting the y by itself. So we still need to be able to take derivatives of these functions, in which case we would now be able to use this technique, which is called implicit differentiation. Um, and we'll be talking about it implicitly because it's happening kind of within the function. Um, and I guess it's important to note what we've been doing is technically called explicit differentiation. So if you ever just hear the word differentiation, you're told to differentiate something. Most of the time, if it just looks like a regular old function y equals, you will just be explicitly differentiating. We just don't feel the need to say that because it's just kind of implied. Explicit is implied. Implicit is when you have to do that because you have kind of no other option of being able to differentiate it. All right. So that's just kind of an introduction into why implicit differentiation is different from explicit differentiation and how it's important. I also want to note this is kind of a me thing. This is again how I was taught and how I think that it's a little bit easier to recognize. You don't have to do this, of course. So when I use implicit differentiation, especially throughout this lecture, it's my recommendation and what I will do. That when we're solving something, we will be writing either dy dx or y prime, and you'll see where this will come into play once we get into the problem solving strategy and then going through some examples. But when we do have to write these, there are times in a problem where we may have multiple dy dx's or multiple y primes, and we're looking to solve for that specific variable because we're trying to differentiate it. And it's my recommendation that we put a box around any dy dx or y prime. Now, again, they're the same thing. We went over the notation and everything like that. It's really just a difference of which one you like better. I'm not going to tell you which notation to use. It's up to you. So I put a box around them so that we don't lose track of those variables. It's very easy if you have a y next to a y prime to think it's the same exact thing, and then all of a sudden your answer is wrong because we've forgotten a y prime. So if you put a box around every single time you have a y prime or a dy dx, it makes it significantly harder to forget about any of them. You see where every single one is, and I'll show you exactly what I mean. All right, so now we can actually go ahead and get started into the introduction into how exactly to solve, given some function that we can't typically solve using regular explicit differentiation. So I'm going to move my little face down to the bottom because we've read that. So to perform implicit differentiation, we're defining y implicitly in terms of x, so we won't again have y equals, we'll have some function where y and x are just kind of like intermingling. So step one, take the derivative of both sides of the equation. All right. Now, typically when you're taking the derivative of x, and this is something that I did write down a little bit earlier, but like not necessarily today, but in a previous lecture, I believe when I was talking about notation, if you have the derivative with respect to x, because we're always doing things with respect to x, if you have the derivative with respect to x of x, technically, we know that this is 1, but also why is it 1? Well, this is also multiplication. A derivative, you could think about bringing this up here, and this is dx over dx. But dx over dx is the same thing over itself, which is just 1, right? But now, if you're taking the derivative with respect to x of y, you can't do that. Y and x don't cancel out. They're not the same thing. And so what you get is you get dy dx. And so this is a justification as to why anytime anytime you take the derivative of anything that has a y in it, when you take the derivative of a y, I know I'm repeating myself, but this is important. You have to write dy dx multiplied by that term that you just took the derivative of that has a y. And this is the reason why, because when you take the derivative with respect to x of a y, you don't get 1. That's why we don't have to write it when we take a regular derivative. You instead get dy dx. All right. So keep in mind that y is a function of x. So again, this is like d over dx of sine is just cosine because we're taking the derivative with respect to x, and this is just of x. But now, if you instead looked at the derivative with respect to x of sine of y, well, we know the derivative of sine is just cosine, so we're going to take derivatives just like we normally would. But then the only extra step is going to be if you took the derivative using chain rule, which we just covered, of y, well, the derivative of y is 1, but it's not just 1. It's 1 dy dx. So we have to multiply this term by dy dx. So that's just a note that's not necessarily like part of the problem solving strategy. So this right here is the first step. Take the derivative of both sides. Keep in mind that y is a function of x. Step 2, rewrite the equation. I should probably have a highlighter instead of an eraser. Rewrite the equation so that all terms containing dy dx are on the left, and all terms that do not contain dy dx are on the right. All right, this is very important as well. So we're moving all terms with the thing that we want on one side and all terms with the things that we don't have on the other. And then pretty much it's going to be the same exact steps every single time. Once you have all the terms with dy dx on one side, you're going to factor out the dy dx. And then you're just going to divide both sides by whatever it is that you just factored out, which will just leave you with dy dx. All right, so the hard part is going to be the differentiation aspect and making sure that you remember to multiply in a dy dx every single time you take the derivative of a y. So like if you have xy and you're trying to take the derivative, you have to remember that's a product rule. And when you take the derivative of y, you have to write dy dx. All right, so let's go ahead and do an example. All right, this is a pretty straightforward example. This is going to be a circle with radius 5. If you recognize that formula, centered at the origin, actually. You don't need to know that, but just a fun fact. So assuming that y is defined implicitly by the equation this, find dy dx. Typically, you won't see defined implicitly. You'll just look at this and you'll understand that it is defined implicitly. Could you solve for y? Yes. But when you solve for y, you have to take a square root, which means that you have a plus and a minus. So now you're creating two equations. That becomes way more difficult than it has to be. That's why we're going to want to use implicit differentiation. That'll save us so much time. So we're going to take the derivative as usual, like I said, but then every time we take the derivative of a y, we just need to multiply that term by dy dx. So the derivative of x squared is just our regular derivative, which is 2x. Derivative of y squared, we use the same exact rules we always do. So that's 2y. But the derivative of y is dy dx. So I'll write dy dx. And this is where I put a box around it just to show that I know exactly where it is. Again, this part you don't necessarily have to do, but I think it really helps in terms of just solving. Equals. And then a big thing that I notice sometimes is that when we see 25, sometimes we'll just leave 25, but we have to remember to take the derivative of 25, and the derivative of a constant is just 0. All right, so now we've taken the derivative of everything, and we're looking to solve for the derivative. Because if we remember, I'm going to do a little example up here. If we have like y equals x squared, we'll just say dy dx, because we've taken the derivative, equals 2x, right? So we've still solved for dy dx, but we've solved explicitly, so it's a little bit easier. Here, we're still solving for dy dx, but it's implicitly, so it's a tiny bit more difficult. We're still trying to accomplish the same thing, though. All right, so now we're trying to solve for dy dx, and it's just like solving for any other variable. We'll move everything we don't want to the other side. So we get 2y dy dx, and again, I put a box around it, equals, and we'll subtract 2x. And then the last step is just using our typical rules of algebra, which will be dividing by our 2y. So we get dy dx, and at this point, I will get rid of the box just because it's by itself. I mean, it's not wrong if you leave it, but it's not necessary anymore. Equals negative 2x over 2y, which we can cancel out the 2's and say is just negative x over y. All right, we haven't been given a point or anything like that. If we were, we could plug that in. But from our given equation, we've now found that dy dx is negative x over y. All right. We can also find a second derivative when we're using implicit differentiation. Now, the key is that typically if we were to have a second derivative, right? So let's go back to our little example that we had up here, which was y equals x squared. Then you could have dy dx is 2x. Well, taking the second derivative, you would take the second derivative of the first derivative, right? So you'd have dy over dx, but then the second derivative is d squared y over dx squared. And when you take the derivative of 2x, you just get 2. All right, so the key when you're looking for a further derivative using implicit differentiation is there's a couple ways that you can do it. You don't have to necessarily do it the way that I'm saying it, but again, I'm trying to give you the quickest, easiest way to do it. Find the first derivative, solve for the first derivative. And then once you have the first derivative written out like this, it's very easy to get to this next step because that is just explicit differentiation. So you can use implicit differentiation twice if you'd like. I'm going to go back to this last slide here. So this right here is the same exact question, except now it's asking us to find the second derivative. So if you'd like, you can leave it like this and you can take the derivative again, in which case you would get a second derivative when you take the derivative. This would be a slightly longer and drawn out process though. So my suggestion is get the first derivative, and then the second derivative is just explicitly differentiating the way that you normally would. All right, so let's go ahead and use our first derivative. We don't need to resolve for that. So dy dx equals negative x over y. All right, so now it's very, very easily, once you have your first derivative, to just find the second one explicitly, except it is technically implicit because we do have a y in there, but it's, I don't know, it's kind of a combination. So now we can say d squared y over dx squared equals, and this is just going to be a quotient rule. So remember, the quotient rule is low d high minus high d low over low squared. And if you'd like to assign an f and a g to that, take the derivatives off to the side and plug it in. I definitely encourage you to do that. I'm going to just use this little, I don't know exactly what you want to call it, a slogan. I don't know. Again, I don't do English. I don't know the proper word for that. So if you want to use this little saying here, I guess we'll go with that word. That's how I'm going to do it. So we'll have a minus out front. I'll just leave that there. All right, so low is just our denominator, so I'll keep a y. D high, so the derivative of the numerator, derivative of x is just 1, so I can write times 1, minus high, which is just x. D low, so this is where we have to be careful. The derivative of y is just 1, but it's not just 1, it's 1 dy dx, and I'll put a box around that, all over low squared, which is y squared. All right, so now what we see is we have a first derivative within our second derivative. And that might look a little bit confusing at first, but the cool thing is that we know what our first derivative is already. We solve for that. We solve when we found the first implicit differentiation question. So all we have to do is plug in our first derivative. And that's why I think it's a little bit easier to do it this way, because either way, you'd still wind up with the first derivative. You would just have to solve for it later on. But if you do it this way, it's a little bit easier to not have to do multiple implicit differentiations with like a whole bunch of rules and then also solve after. It's a little bit more convoluted to do it that way. So now we can just say negative y minus, so I multiplied the y by 1, and then I'm going to do x times, this is our dy dx here. So negative x over y, all over y squared. And you don't have to simplify it. In fact, I encourage you not to simplify it most of the time. But since this is such an easy simplification, I will just go ahead and say this is the same thing as y. Minus times minus is plus x squared over y, all over y squared. And of course, there are ways to simplify this as well to make it into a nicer looking fraction, but that's not what I'm looking for you to do. What I'm looking for you to do is just find a derivative. All right, so this is a good answer when it comes to finding a second derivative using implicit differentiation. All right, now we have an actual graph that is a fun little shape. So this is called the folium or leaf of Descartes. It looks like this. That's just a little fun fact. And it specifically has this function right here, this equation. And we're trying to find the equation of the tangent line to this graph. And something specific to note about it is that there's no way of solving this explicitly, because if you tried to factor out a y, you'd still be left with a y times a y, and there's no nice way of doing it. So the only way to find any form of an equation line, of a tangent line is in fact to use implicit differentiation. And here we're looking to do it at this point right here. All right, so let's go ahead and find our derivative. So we'll go ahead and take the derivative. I'll rewrite the original plus x cubed minus 3y equals 0. Xy equals 0, just to have it a little bit closer to where we will take the derivative. And we can go ahead and take our derivative. All right, again, the same way that we always would. So derivative of y cubed is 3y squared. But because we took a derivative of a y and not an x, we need to multiply this by dy over dx, and I'll put a box around that. This is especially important in this question because we will have two dy dx's. All right, let's take the derivative of x cubed. That's plus 3x squared. We don't need to write anything because that's the derivative with respect to x of an x. And then we have this product rule. All right, it's very important to recognize this as a product rule and not just take the derivative with respect to a single variable. All right, so we remember the product rule goes something like f g prime plus f prime g, where we can define one function as one part of our product and one function as the other part of our product. I also write it as first, that's a 1, times the derivative of the second plus second derivative of the first. So either one is absolutely fine. I'm again going to go ahead and use the first derivative of the second plus second derivative of the first. And I'm just going to go and group like this so I know what my first and my second are. So I'm going to say minus 3x is my first, and the positive y is going to be my second. All right, so that gives me first, so I can just rewrite minus 3x times the derivative of the second. So the derivative of y is dy dx. So now we see that we have two dy dx's, and that's why it's important to remember that we have two of them, plus second, which is y. Because we're just writing y, we don't need to write dy dx. We're not taking a derivative. Derivative of the first. So the first is negative 3x. The derivative of negative 3x is just negative 3. And this is equal to 0. So the derivative of 0 is obviously just 0. All right. Now, of course, when you're just asked to find a derivative, I always say don't simplify, but this you do need to simplify because we're actually looking to find dy dx. So we will have all of the terms with dy dx on one side and everything else on the other. I'll leave 3y squared dy dx, and I'll leave the minus 3x dy dx. And I'm going to move to the right side this 3x squared and the minus 3y. So this equals, I'll go ahead and move this one first. So minus 3y, add it to the other side, gives us positive 3y, and I'll subtract 3x squared. Now I can go ahead, I see that I have two of the same thing, which means that I can factor out a dy dx. So dy dx, and when I factor that out, I'm just left with whatever is next to them, which is a 3y squared minus 3x equals whatever's over here. It's whatever we had before. All right, and the last step is obviously just to divide our remainder of what we don't want on the left-hand side over to the right-hand side. So we have dy dx equals 3y minus 3x squared all over 3y squared minus 3x. All right. So now, let me just double check. All right. We're not just looking for the derivative, though. We're looking for the equation of the tangent line. So we remember that derivative is slope. So if we're looking for the slope, we remember the equation of a line is y minus y1 equals mx minus x1. We need the slope. The slope is the derivative. We need the slope at a specific point. Well, they gave us that specific point. So we can go ahead and plug in this point. And I'm going to use that notation that I introduced a little while ago. So this is an evaluation bar. We just put a bar next to it. Evaluated at 3 over 2, 3 over 2. And what that means is I'll plug in 3 over 2 to my x and my 3 over 2 to my y. So this is equal to 3 times 3 over 2 minus 3, 3 over 2 squared over 3 times 3 over 2 squared minus 3 times 3 over 2. Now, I don't want to do all of this multiplication out, and there's actually a really easy way to solve this without doing pretty much any work. I notice that I have a 3 times 3 over 2 squared in the top and the bottom, and the same times 3 times 3 over 2 top and bottom, and the only difference is that the positions are switched. So all that means is if I factor out a -1 from either side, I can then go ahead and switch the positions of those two terms, and then I get the same thing on the top and the bottom. So what I can do is I can factor out a negative, and I could have 3 times 3 over 2 squared minus 3 times 3 over 2 over the denominator, which I'm not going to touch. And what you notice is the top and the bottom are now the same except for this -1, and so the slope is -1. All right, just a quick, easy way of doing that without having to use a calculator. Now we're looking to find the equation of the line. We have the slope, we have a point. I'm going to go ahead and just write the equation up here because silly me ran out of room. So we have y minus, this is x1 and this is y1. So y minus 3 over 2 equals m, which we just solved for -1, x minus 3 over 2. And this is an appropriate equation for a line in my class. All right, let's go ahead and try another one, finding an equation of a tangent line given x squared minus y squared equals 16 at 5, 3. This is not a circle because there's not a plus, it's a minus instead. All right, so let's go ahead and use implicit differentiation. So we see that 2x has, x squared has a derivative 2x minus y squared has a derivative 2y, but we have to consider that we've taken the derivative of a y implicitly. And now I'll show you without using dy dx, you can also, if you prefer to do y prime, you can. I don't like this notation because sometimes that gets confused with the regular y's if you're not careful. That's when the box comes into play. But I'll show you this in case this is what you prefer. All right, this is, again, the same thing as dy dx. So minus 2y, y prime equals the derivative of 16 is just 0. All right, now we're looking to solve for our y prime. So I can say minus 2y, y prime equals, I'll subtract the 2x. And then I can divide the -2y to the other side and I get y prime equals -2x over -2y, which when I divide the -2's away, I just get x over y. All right, but again, this is not what we're stopping at. We're looking for the equation of a line at 5, 3. So we're evaluating this at the point 5, 3. Well, x is 5 and y is 3. So I can just go ahead and plug those in. So we know our slope then is 5, 3, 5 over 3. We also know that this is x1 and this is y1. Therefore, if we know that y minus y1 equals m, x minus x1 is the equation of a line, we can just go ahead and plug it in. So y minus 3 equals 5/3 x minus 5. And this is a fine answer. All right, I think that might be the last one. Yep. All right, so that is the last one. I guess I should also note that it will seem like we're going out of order. It's because we are. So we're going to do 3.8 before we do 3.7. You'll see why once we get to 3.7, we're going to use, I'm going off book for 3.7. I'm not going to necessarily follow the textbook. We're going to use implicit differentiation, but obviously 3.7 doesn't have implicit differentiation yet because this is 3.8, in which we are doing implicit differentiation. So the next one should also be not too long. Again, if you have any questions, let me know, and I will see you next time.